Hi, I'm Vaidehi Srinivas, and I'm going to be talking about memory bounds for the experts problem, which is joint work with David Woodruff, Neil Zhou, and Samson Zhou. So prediction with expert advice is a classic problem of sequential prediction. So think of yourself as trying to predict some outcome, maybe a binary outcome, and maybe it's the weather. So every day we want to predict whether it's going to be sunny or rainy. So with no information, this is difficult, but you're given access to a set of experts who are just people with opinions. And on each day, they'll tell you whether they think it's going to be sunny or rainy. Based on what they say, you make your prediction, and then the actual outcome is revealed to you. Now you play this again for another day. They tell you what they think, you make your prediction, the actual outcome is revealed. And then you continue playing this for a series of days. We're going to call the number of experts in our set N, and the number of days that we play for capital T. So what does it mean to do well in this problem? In general, predicting the future is impossible. So if all of the experts in your set are really bad at predicting this outcome, we can't expect you to be good at predicting this outcome either. So we judge our algorithm based on regret. Regret is going to be defined to be the number of mistakes that our algorithm makes more than the best expert over the number of days that you play for. This is also called average regret as opposed to additive regret, but this is the notion of regret that we're going to focus on for this talk. So there's a classical algorithm for this problem is the multiplicative weights algorithm. And so in this algorithm, we initialize a set of weights, which you can think of as a confidence that we have in each of our experts. So when we first start, we don't know which experts are good and which experts are bad. So we give them all weight 1. Then they give us their predictions, and the algorithm is going to predict a weighted majority of their predictions. When the actual outcome is revealed, now we have a chance to learn which experts were good and which were bad. So what we're going to do is any expert that was wrong, we're going to cut their weight in half, and all the other experts, we keep their weight the same. Now we play the next day. On the next day, our weighted majority says rain, so we predict rain. The actual outcome is revealed, it's rain. Expert 3 was wrong, we cut his weight in half, and then we play again. Now the weighted majority is sun, we predict sun, it's rain. We cut the weights in half of experts 1, 3, and 4. And so on. At the end of the game, we can see that our algorithm made 2 mistakes, whereas the best expert is this red expert over here only made 1 mistake, and we played for 4 days. So our average regret is 2 minus 1 over 4, 1/4. So the multiplicative weights algorithm is a very classical algorithm, and there's standard guarantees for it. This version that we just saw is the deterministic weighted majority algorithm. And we can see that the number of mistakes that deterministic weighted majority makes is around 2.5 times the number of mistakes of the best expert, plus this log n term. But log n, remember n is the number of experts in our set. So this doesn't scale for the amount of time that we're playing. You can think of this as like a fixed startup cost. So putting this in terms of regret, which is the quantity we care about, this has regret of O of m plus log n over t. And you can tune this algorithm and randomize it so that for any epsilon greater than 0, we can construct an algorithm A such that the expected number of mistakes that this algorithm makes is 1 plus epsilon times the number of mistakes that the best expert makes, plus again, this ln n term. And remember again that this ln n doesn't scale with the amount of time you play for. Picking the right epsilon, we can show that you can get a regret that looks like root log n over t. And in fact, this is tight. Information theoretically, you can't do better for prediction in this problem. Okay, so experts problems and algorithms for the experts problems have many different applications. Maybe the most classical application of it is for ensemble learning in the famous AdaBoost algorithm that takes a bunch of weak learners and turns it into a strong learner. You can also use it for online convex optimization, for forecasting, like our example, in portfolio optimization, and some of the early work on these kinds of multiplicative weight updates come from solving for equilibria of zero-sum games. So where's the room for improvement? This is a classical problem, classical algorithm, it's tight. But multiplicative weights keeps track of the number of mistakes that every expert has made so far. And this takes omega n memory. So maybe if your expert set looks like this is fine. But if your set of experts is really large, this can start to become more of a problem. So the question is, can we solve this problem with less memory? And spoiler alert, if you want to get the same regret bound that you do for multiplicative weights, you can't. We'll show that you need omega n memory. However, if you're willing to compromise on this regret a little bit, you can actually trade off your regret with the amount of memory that your algorithm uses. So to talk about what it means for an algorithm to use a lot of memory, formally we use the streaming model. Informally, this is how you can think about the streaming model. So on every day, your algorithm or you wake up with no memory of what's happened so far, except for a note that you've written about previous days that's at most S bits. Then you see the expert predictions for today, you make your prediction, the outcome is revealed, and then you write a note for future days that's also at most S bits, and then you fall asleep and forget everything. We could also give a stricter condition that says between the expert predictions that you saw today and the outcome, you can also only remember S bits. And we'll show that in the weaker setting where you're allowed to remember as much as you want in this part, our lower bounds hold. And in the stronger setting where you have to keep at most S bits between the predictions and the outcome, our upper bounds hold. So actually, our lower bounds hold for a more general setting, our upper bounds hold for the stricter setting. This complete sequence of T days is the data stream. So prediction outcome 1, all the way up to prediction and outcome 2, T. And we're going to think of two main streaming models. The first is the arbitrary order model. So in this model, an adversary chooses the predictions and outcomes to be tricky for the algorithm. In the second model is the random order model. In this model, an adversary chooses the predictions and outcomes to be tricky, and then the order of the days is randomly shuffled. So in this picture, you can see that maybe the days come in random order, but on a particular day, the predictions and outcomes for that day are chosen in relation to each other by the adversary, so they can be related. So our results, first we have a lower bound. Our lower bound tells us that any algorithm that achieves average regret delta in expectation must use omega n over delta squared T space, even for random order and IID streams. So to give some context to what this bound means, to match our multiplicative weights regret, we need regret approximately root 1 over T. We're ignoring some log n terms here, but throw away the log terms just for intuition. So this tells us that to match this regret, we need to use omega n space. But potentially, we could do much better if delta was a constant. This lower bound doesn't rule that out. For a constant delta, maybe we could do as well as n over T space. And our upper bound for random order streams tells us that actually this lower bound is tight for random order streams. So for a target delta, where we have a bound on delta, but basically this tells us as long as delta is basically larger than the information theoretic bound that already exists for multiplicative weights without the memory constraint, our algorithm achieves average regret delta in expectation using n over delta squared T space. So this matches our lower bound. And in fact, so far we've been talking about our costs being either 0 or 1 on each day, but this can handle experts that incur a cost that's between 0 and 1 on each day. And then finally, for arbitrary order streams, we look at the regime where the best expert makes a slightly sub-constant fraction of mistakes. So we say M, which is the number of mistakes the best expert makes, is at most delta squared T over log squared n-ish. So as long as this is true, then again for a target regret delta, which is above our information theoretic bound, our algorithm achieves average regret delta in expectation using n over delta T space. So in this regime, we can actually beat our lower bound. And this tells us that the hardness of the lower bound comes from the regime when the best expert makes a large number of mistakes. Because if the best expert makes even a slightly sub-constant fraction of mistakes, we can actually beat the lower bound. So now I'll give you a sketch of how the proof of our lower bound goes. So to do this, we're going to reduce from a communication problem to our streaming problem. Then we'll show that the communication problem is hard, so our streaming problem is also hard. In particular, we're going to look at problems in the Blackboard communication model. So the Blackboard communication model is this one on the right. And you can think of there's a bunch of processors, 1, 2, 3, up to T, that are working together to solve a problem, but each of them only has part of the input. And they want to bound the total amount of communication it takes for them to solve this problem. So the way we're going to measure communication is there's a Blackboard, and any processor can write something on the Blackboard, and that costs them however much they wrote. But once it's on the Blackboard, all of the processors can see what's on the Blackboard for free. We can also think of the streaming model as actually being a communication model, where there's a bunch of days, and each day does some computation on its part of the input, and then it sends the state to the next day. And then that day does some part of the computation on its input, and then it sends the state along. And since this is only going in one way, whereas the Blackboard model allows multiple rounds of communication, or doesn't specify the order of the communication, the streaming model is actually a more restricted version of the Blackboard model in some ways. So this tells us that any S-space streaming protocol, we can turn it into an S times T communication Blackboard protocol, where processor 1 runs what day 1 would have done, and then whatever state comes out, it writes it to the Blackboard, and then processor 2 sees that, and then it does its update and writes the state to the Blackboard, and so on. And this tells us that proving a Blackboard lower bound gives a B over T streaming lower bound as well by the contrapositive. So now we're going to design a communication problem that takes a lot of communication. Then we're going to show that a delta regret expert prediction algorithm can actually solve this problem. And that's going to tell us that the delta regret expert algorithm is going to need to have a significant streaming space. So the basic building block of the communication problem that we're going to build is this delta distributed detection problem. So in this problem, think of each of your processors 1 through T has the outcome of a coin flip, okay? And they're all from the same coin. And together talking to each other, the processors need to decide whether they're in this case where all of these coin flips came from a fair coin, or they're in this case where all of these coin flips came from a better coin, which has probability of heads 1/1/2 plus delta. And this problem has a communication lower bound of omega 1 over delta squared, which was shown by Braverman et al. In their paper in 2016. So now we can put together this problem into, this is like the small building block for a communication problem, and we can build a bigger communication problem built based on this building block. So now we're going to introduce the delta diff disk problem, in which we distinguish, but we have our T processors again, and each of them has the outcome of a coin flip from coins 1, coin 2, coin 3, up to coin n. And they need to talk to each other and decide whether they're in the case where all of these n coins were fair coins, or they're in this case where n minus 1 of the coins were fair coins, and one of the coins was one of this slightly better coin. Intuitively, it seems like they now need to solve the one coin problem on every single index. And in fact, we can show that this is the case using a direct sum framework of the same version that based on what Bar-Yosef et al. Used in their 2004 paper. And we can show that this requires omega n over delta squared communication. Remember, 1 over delta squared is what we need to solve one coin. And so n times that, because we need to solve it for every index. Now, this problem is a communication problem that requires a decent amount of communication. And we're going to show that we can solve this using a delta regret expert prediction algorithm. So here's how we're going to reduce it. We can think of these coins as being experts and the processors as being days. And now we're hoping that this better coin is going to look like a slightly better expert, whereas these all fair coins are going to look like a bunch of experts that, they're predicting randomly, so they don't really know what's going on. So, but we know that this better coin gets heads more than tails. So we're going to fix our outcome to just be heads on each day. This is like a fake outcome that we're adding to our problem. And now, what happens if we run a delta regret expert prediction algorithm on these two inputs? On the all fair coins case, we're going to say the best expert makes mistakes like half of the time, right? Because it gets heads with probability 1/2. And in this one better coin case, we have this better coin that's going to make mistakes half minus delta of the time. So it's doing better. So if we run a delta regret expert prediction algorithm on the one better coin instance, then it's going to make mistakes less than half of the time, which is good. We'd like to say that if we run a delta regret expert prediction algorithm on this all fair coins case, that it will do badly. And it'll make mistakes at least half of the time, right? But unfortunately, as is, we can't actually say that, because our delta regret algorithm gives us a guarantee that says if the input is good, it will predict well. It doesn't say that if the input is bad, it will predict badly. And in fact, even a really simple algorithm just always predicts heads will get 100% accuracy in both the one better coin case and the all fair coins case. So running a delta regret expert prediction algorithm on these kinds of instances won't necessarily let us figure out which case we're in. So we fixed this by adding a mask to the predictions and outcomes with a fair coin flip. So here, think of maybe our coin flip came up heads for day one and processor 1 and processor T, and then it comes up tails for processor 2 and processor 3. So on these days when it's masked, we flip the outcome, but we also flip all of the coin flips. So this transformation will preserve whether a coin flip matches its outcome on a given day. So that means that here the best expert still makes mistakes half of the time. Here the best expert still makes mistakes half minus delta of the time. And so a delta regret algorithm will still make mistakes less than half of the time in the one better coin case. So all of that is still good. We still know that a delta regret algorithm will do well in this case. Now, for the all fair coins case, we now know that the outcome is a uniformly random coin flip. And it was independent of the predictions before, and it's still independent of the predictions. So no algorithm can predict a uniformly random coin flip more than half of the time. So no algorithm can make mistakes less than half of the time. So now we have our reduction. We run a delta regret expert prediction algorithm on our instance. If it's doing really well, then we must be in the one better coin case. If it's doing badly, we must be in the all fair coins case, and we can tell these two apart. Finally, we can bound the streaming state size of our delta regret expert prediction algorithm. So if S is the size of the streaming state of this algorithm, then this protocol for delta diff dist uses T, which is number of processors, times S plus 1 bits of communication, where on every day we have to write the streaming state to the Blackboard, and then also a bit for whether or not we were correct today. And recall that we said that this delta diff dist problem takes omega n over delta squared communication in the Blackboard model. So this means that our streaming state must have size omega n over delta squared over T. And this gives our lower bound. So now I'll give you a sketch of how the upper bounds for our problem look. And both the random order upper bound and the arbitrary order upper bound are going to be very similar in flavor. They're both going to be sampling-based algorithms. So our goal is that given a guess for M, which is the number of mistakes that the best expert makes, we want to make at most M plus O of delta T mistakes. We can get rid of this guess for M in the random order case by using a prefix of the stream to kind of estimate what M should be. And in the arbitrary order case, we assume that this M is kind of sub-constant in delta T. And so then it's not going to be the dominating term. So we can just use that itself as our guess for what M is. And now we're going to use a black box call to multiplicative weights. So recall our guarantees for the multiplicative weights algorithm. We said that the cost of the algorithm incurs is at most 1 plus delta M plus ln n over delta. This is something where we can choose delta. Where M is the cost of the best expert. And we can think of these two terms as being the startup cost and the ongoing cost. So the startup cost here is because it's ln n, it doesn't scale with the number of days we play for. Whereas its ongoing cost is as the best expert is making more mistakes, this ongoing cost is going to go up. So now here's our strategy. We're going to run multiplicative weights on a randomly sampled pool of n over delta squared T times ln n experts. Okay, and if and when every expert in the pool has average mistake rate M over T plus delta greater than that, recall this is kind of the rate of mistakes that we're going for. If every expert is doing worse than we're hoping for, then we're going to resample and start over. So the total cost is going to be the cost for running multiplicative weight, these ongoing costs for all of the pools, plus the startup costs for all of the pools. And the ongoing cost in every pool, we know that we're only running these pools as long as there's an expert that's doing pretty well, better than our target rate. So our ongoing cost is going to look like what we want it to look like. And then there's these startup costs. And this is potentially a problem, right? If we keep throwing out our pools too much, then we might have to pay the startup cost many, many times. And so we need to bound the number of rounds that we sample for to show that the startup costs that we pay over time is not going to be too high. Visually, you can think of it like this. So again, remember, our idea is we're going to run multiplicative weights on a randomly sampled subset of experts. And we're setting a threshold of what we think is the acceptable error rate. And if all of the experts in our pool have gone above this threshold of acceptable error rate, then we throw out the pool and we resample. So maybe this is our first pool. We choose this expert and these 3 experts to be in our pool. And as long as there's one expert in this pool that's doing well, we paid our startup cost to start and multiplicative weights is going to do well. Then maybe there's a day when everyone in the set is doing badly. Okay, we throw them out and we resample our pool. Now we have to pay the startup cost again because we're restarting multiplicative weights, but then as long as we continue in this pool, multiplicative weights is going to do well. Then maybe everyone's doing badly again. We throw out the pool, we restart, we pay the startup cost again, and now the best expert in the set is doing well. So what we want to bound is the number of times we pay this startup cost. Right? We want to say that we won't restart too many times. So how do we bound this number of rounds? Where remember, like in the corner is this thing that this is what we're going for. And we want to bound the number of rounds to show that this is going to be m plus O of delta t. Well, for random order streams, with high probability, once we catch the best expert, we will never resample. Why is that? Because think of this as being a chart of the number of mistakes that the best expert makes over time. So every orange bar is a mistake, and this is how they're distributed over time. Because we're in a random order stream, these are basically evenly spaced. So if we catch the best expert in our pool, then it won't make a big chunk of mistakes very close to when we catch it. It won't cause us to throw that pool out. It'll actually do pretty well uniformly. And so if we catch it, then we'll continue in that pool forever. So the question is, how many rounds can we go before we catch it? Well, the probability that we catch the best expert in a given pool is the size of the pool over n, which is this n ln n over delta squared t over n. And so the expected number of rounds before we catch it is delta squared t over ln n. Now we can plug this into the number of rounds up here. And this tells us that actually the total cost now is m plus O of delta t, which is exactly what we wanted. For arbitrary order streams, we assume that the best expert makes this slightly sub-constant fraction of mistakes, right? But now we can't assume that these mistakes are going to be evenly distributed, right? So maybe they're going to be clumped up like this. And now there are these days are bad days to sample. If we sampled a pool on that day and we caught the best expert, we might still throw it out because the best expert made so many mistakes close together that we thought it was a bad pool and we threw it out. However, since the best expert makes only a few mistakes, then there can only be so many of these bad days. And so even if we sampled on every single one of these bad days, it won't blow up the number of rounds that we play for too much. And so we can still, in this case, show that we'll make m plus O of delta t mistakes. But finally, for our conclusions, to recap our results, we showed a lower bound for the prediction with expert advice problem. We showed a lower bound on space that shows that any algorithm that achieves average regret delta in expectation must use n over delta squared t space. And our construction was actually invariant to random order. So this holds even for random order and IID streams. Then we showed that for random order streams, this bound is tight. We have an algorithm that can meet this bound up to like log terms, as long as our delta is above the information theoretic bound. And then we showed for arbitrary order streams, if we look at the regime where the best expert makes a slightly sub-constant fraction of mistakes, then we can actually beat our lower bound using a very similar algorithm that we use to the random order streams. In terms of future directions, one big question is, can we get tight bounds for these arbitrary order streams? So right now, we don't have a bound that tells us if the best expert makes a constant fraction of mistakes, can we achieve constant regret delta? And then, so there could be improvements to the lower bound here, upper bound. It's not clear. Like, what is the tight bound? And then maybe we can get better bounds when the expert costs have more structure. So for example, if your expert predictions are real numbers that are evaluated against the true outcome with some loss function, maybe knowing this extra structure can help you design a better algorithm and circumvent the lower bound. And maybe we can get better bounds if we had extra constraints on experts. So similarly, if we had more structure, can we get better bounds for these specific cases? So these are all interesting future directions. Yeah, and that's all for memory bounds for the experts problem. Thank you.